the interest we have is really understanding how materials fail and break, as of how they lose function. And the other way around would be what engineers usually like to do. They like to design things for function. We use failure to understand the limits of function, and so sort of the inverse problem, the negative of that problem. And we break materials. We break spider webs. We break other materials like graphene, carbon nanotubes, bone, nacre, and all sorts of different types of structures. And when you break things, when you really look at materials' function and failure to function, clearly that involves all relevant scales. And failure is actually a great example to illustrate this. If you imagine breaking a piece of polymer or paper, when you tear this apart, at the macroscopic scale, you see that the paper essentially falls into two pieces once you break it, or glass shatters, and you see these different pieces of glass. Sort of, if you go down and imagine what happens at the chemical scale, at the molecular scale, and it's clear that at some point you have to break bonds between molecules, between atoms. And so failure is really something that intuitively and visually really invokes multiple scales, all the way from the atoms all the way to the macro scale that you can see with your eyes. And this issue really led us into looking at multiple scales and understanding materials. And we begin describing materials now at the atomistic scale. So we have tools, computational analytical tools, that allow us to start basically describing materials, very complex materials like spider silk or bone or cellular proteins or steel potentially or graphene or even concrete, based on the structure of atoms and molecules. And what's interesting here is that, of course, now we have computational methods that allow us to do this, which really hasn't been, we couldn't do this 10 years ago. So if you go around and you see, sort of compare what computational power has done for us and methods, really is a huge leap. But the other part of the story are experimental studies that can be done, and huge advances have been made in really looking at materials at multiple scales experimentally, which is, in a way, is critical, right? So now you have a tool where you can predict things in a computer simulation, and you can actually probe and test these predictions using experimental studies. And we can pull on single molecules, we can sort of test the shape of molecules, we can probe fibers and fibrils in a human body at the scale and resolution that has not been possible just a couple of years ago. And in our research, we combine these. So we have collaborations and sometimes our own experimental studies where we combine these advanced high-fidelity simulations with what is possible experimentally. And that's an extremely exciting area, which really has fascinated me and has really made me even more excited as we go on, because we can do so much more. And I think the more we discover, the more we know how these methods actually work and how they can predict new phenomena, how they can solve phenomena in nature and engineering and technology, the more we can apply them to additional problems. And sort of the boundaries are really blurred now between basic science, physics, chemistry, engineering. So computationally, we have, when you describe materials, really from a molecular perspective. So you have sort of, traditionally you have the chemists that tell us this is the molecular structure of a material. Then you have the engineers tell us, well, this is the strength of a material. And there's a huge gap between these. So you cannot predict using traditional models. If you go to college today, you wouldn't learn how to predict the strength of a polymer or metal or steel or any kind of material from knowing just the chemical structure. There's obviously something between. And these what's in between are scales that are huge, vastly different scales. And you can compare this with the size of the universe or distance to the moon. There are orders of magnitude in length scales between 10 to the minus 10 angstrom, which is the scale of a chemical bond, and something, say out of a meter or 100 meter, like an airplane or ship or building. So now you get 10 to the minus 10 to the minus 10 to 10 to the 0 orders of scales difference. And how do you bridge these? So there, obviously, if you simulate materials, right, and you say, let's simulate every single atom, so now you got trillions and trillions and trillions of atoms that you need to simulate, and that's beyond the capability of a computer, right? So you would basically have to predict the motion of every single atom. Now that sort of problem requires us to think about new ways computationally and modeling-wise how we deal with this problem. And so how we can do this now is we can still use really big computers to simulate ever larger systems, right? Larger molecules, more complex molecules, better models for the chemical bonds between the molecules. But we also have methods now in which we can upscale things. So we group atoms and molecules into functional units, right? So you can assume that several molecules form a fiber, and this fiber has a certain behavior, and then we can model the behavior of the fiber embedded in a larger group of fibers using a computationally simpler technique. And that technique really, it's called multi-scale modeling. And what's unique about this technique is we can base it really on the atomic scale interactions. So we start in the beginning from the description of chemistry. We put together atoms and molecules. We simulate how they behave. We then identify emerging behavior in these groups of atoms and molecules, and we coarse grain this. We call it coarse graining, computationally simplifying the interactions. In sort of similar way as you imagine, if you imagine a chemical bond, which you in chemistry sometimes think of as a spring, in a simple way. Now, in a quantum mechanical description, the spring really comes from electrons interacting with the atom core and other structures in the system. So these interactions, very complex features, really can be described by a simple spring, right? And this is something that we can do again and again at different scales to solve this problem. So big computers is one. New ideas, understanding about how we can model chemical bonds effectively without actually solving all the complex quantum mechanical equations is very important as well. And then we need to validate, and that's when experimental studies again come in, because we can predict things, we can build models, but if we don't have a good tool of actually making sure that what we're doing is correct, we need experimentation at different scales that tell us that this approach of actually grouping atoms into a functional fiber that we have identified makes sense. We need to prove this, and that can be proven by using experimentation. And so we use this systematically. Once we gain understanding for systems, wide variety of systems, we can apply this to even more systems, right? And then we have confidence that the tools we have are actually predictive. And so we now have various examples where we've actually used these types of computational predictions for materials like carbon nanotube-based fibers. We've used it for spider webs, other protein materials, engineered materials, and we're very successful actually in predicting phenomena that we can see in a simulation and an experiment. And there's sort of advantages of both worlds, right? We can see things in experimentation, we can see them, and there's immediate proof that that really happens. In a simulation, we might be able to see additional things. We might be able to see very low resolution motion of atoms, which are very hard to see experimentally. We can design conditions in a simulation that we cannot easily probe in experimentation, right? Extreme pressures. We can invent material behaviors. We can probe what if silk would behave in a very particular way, which helps us really understand the system in a very systematic way. So that combination of experiment, simulation, the talking between them, validation, and asking questions that again are informed from the simulation results, from the experimental results, is what drives the research. And what we do in the end, by combining then simulation experiment, we can build theories. And that's sort of the final goal always, is that we don't want to end just by sort of putting forth some predictions we've made or some observations we've made, but actually we like to understand things, and you can build a model, an equation or a graph, something of that kind, mathematically actually describe the essence of what you see in a material. And that's usually the goal. Most projects, most the things we look at in our lab work like this. So we start simulation experiment, simulation, pushing things forward, eventually ending with a model that captures really the essence. And that's what's useful for engineers in the end.